Well, thank you very much, Manfred, for such a nice introduction, and I'm really, flattered that you invited me. I I wasn't sure if people really interested in this and so on, but so I really appreciate it. And basically, so about myself, I'm geologist, and I do a lot of work in natural hazards, coastal erosion, landslides recently, and I also do. I mean, in the past, I did some work in geochronology, geomorphology. That's all stems from my work. I came to United States from Ukraine in '89. In Ukraine, I used to work on landslides, coastal erosion and landslides. So last 15 years basically I was following the same thing, coastal erosion in Alaska and then landslides in Caribbean region, Central America. So I work at Lehman College. It's one of 13 colleges, City University of New York, and the whole work started about landslides with a grant from Central American funding agency. It's a part of United States NSF. So they funded our work in Guatemala, and then I kind of get back to my field again, to landslides, and it's all started from there. So my talk is about can we predict landslides in real time? And as you know, it's a challenge. We still can't really predict landslides. It's very difficult. So how we can do this? Let me see. So we can start with why we need to do it. What is the reason? And the reason is because knowing hazard risks can help people make decisions. And I think that's very important. So people in communities can make decisions what they want to do. They want to leave, they want to stay. And risk is usually a probability of event multiplied by consequences. So consequences, damages to people, property, economics. And probability of event is how can we be sure that event is going to happen, right? High probability, low probability. So real-time predictions can help real-time decisions. And that's one of the, I think, important issues when you have a disaster and the people are involved. So this is a picture of 100 years of hurricane activity in Caribbean Basin and Central America. So you see United States, you see Atlantic Ocean, Pacific Ocean here, and Guatemala. And you see this all tracks, how they fill up the region. So this is the Caribbean Basin, and Central America here. And there is two systems, one from Pacific, one from Atlantic. So they kind of collide together and produce enormous amount of hurricanes. Okay. So when we talk about recent near real-time predictive tools, this is one from Earth Observatory, NASA, and it was developed by scientists who tried to link landslide hazards in real time, and the model is linked to GPM. So it uses IMERG data. It's integrated multi-satellite retrievals data, and basically it's following GPM data every 30 minutes in the world and telling us that's potential places in the world where you can expect landslides because of increased rainfall activity. And so this is first time we can see something like that. What is missing in this model? So the model is great. It's really, worldwide and using global data. So it's really nice step forward. However, you can't apply it, in my opinion, again, for operational use, because this model doesn't have regional specifics. And when we talk about Caribbean Basin or another region with a strong cyclonic activity, then we have these issues. One of them is a hurricane path orientation, wind direction. So that affects spatial distribution of moisture. And I just call it like a hosing effect, like you take a hose in your garden and you start putting water on your plants and you move it around. So moisture distribution is not the same everywhere. unless you have like a big system and it covers the whole thing, but usually it's not. So depending on the wind direction and hurricane orientation, how does it go, you can have different spatial distribution of moisture. So that's one aspect. The second one is that you get selective impact of wind-driven rainfall. We're going to talk more about this later on terrain. So it's a relationship between slope aspect and moisture distribution. In many books, you can find it as orographic effect. So, but usually we use orographic effect in terms of like big, mountain ranges like, California, Cascades. So you got Pacific more moist air coming in, and then you get a dry air on other side. But it's also applied in a small areas like small mountains in Central America, have, quite good mountains there. So there's two components: hurricane path orientation, wind direction, and selective impact of wind-driven rainfall. They most likely the key component which influence landslide distribution in Caribbean and Central America. So any other region with a strong cyclonic activity. This is what I saw when we came to Guatemala in 2014 or 15. It's a pattern. So when I saw that, aerial photography from Hurricane Stan, I was surprised to see that a lot of landslides, it's white spots. They're happening only on one side of the valley. So here is, you see the river. So this is a river, right? And then you see a landslide on this side of the valley, but you don't see anything here. And the same thing here, you have a river and landslides occur only on some specific places, but not here. And the same thing everywhere if you look. So you see kind of like a pattern. So why the landslides, don't occur on both sides of the valley? Why it's only one side? And then the second thing here is, this is a Hurricane Mitch, 1988. It's amazing, actually, data set we were able to get from USGS. So they still maintain that server, which, contained data back 1980s about landslides, and it's available to public. You can download it. We got like 11,000 landslides to analyze. And the same thing is here. So you see that the landslides occur on very specific parts of the valley. So it's not like you don't see them here, but you see a lot of them on this side. So the question is also why. It's kind of the same terrain. Geology is pretty much the same. And, the question is what happened here? So this is analysis from data which we collected, and we published paper in 2016 about landslides, hazard, and risk mapping in Guatemala. So simple analysis like, just, you look at histogram. Distribution shows you that most of the landslides occur in this region. So this is, we have it here. It's basically southeast and southern directions. And this is how this event occurred. So the hurricane, as you can see, rotation here. So that's cyclonic activity. That's 2005-10-2. So this is this date. And so this cyclone, actually, hurricane, was coming to Guatemala. And actually, you can see here a Pacific one, which is in other side. So there is another cyclonic activity. But when you look at distribution of wind directions during this hurricane, you can see that a lot of them on this part comes from the north. But then there is also some, movement of the air from the south. So you have kind of like two cyclonic areas here, and then they propagate through the whole country. And the question is, why do you have, that specific distribution of landslides only in, southeastern aspect, orientation of the slope, southeast and south. So that's about Guatemala. This one, Hurricane Mitch, 1988, and you see here is the same, 120, 140, this is southeast. That's report from USGS in 2001 about landslides by Hurricane Mitch. And you can see here like histogram, which basically repeat what we learned from previous study in Hurricane Stan. So there is some kind of a pattern. There is a not very simple thing. And in the paper, this paper, 2016, we did analysis of about like 20 different papers that deal with the distribution of landslides. And there is a pattern of specific locations of landslides during hurricane activity. This is a Hurricane Maria on Puerto Rico. So that's another paper. So this paper is, which we have is basically, you see the Puerto Rico island right here. This is the path of hurricane which goes through the region, through the Puerto Rico. And if you look at a distribution of landslides, in a paper we presented two digital elevation models. One is SRTM, Shuttle Radar Topographic Mission. So that is 30-meter DM. And LiDAR DM, it was close to 1 meter from USGS. And both of them, distribution of landslides, if you look at aspect produced from LiDAR and aspect produced from SRTM, so you're looking at orientations, right? They show bimodal kind of a pattern here. And what you see here is, this is how we try to explain it. I mean, of course, there might be some other explanation, but so here's a hurricane coming, and it looks like a blade, right? Like rotating blade. So when it comes here, you have direction affecting terrain from northwest. Okay, so mainly northwestern, side will be affected by this rotation. When hurricane passes by, you have another effect from south. And so this is what probably could be one of this, like ideas about why do we have this bimodal distribution, just because of that hurricane position. When it passes through the island, it changes directions. And so this, could be an explanation. We are not sure, but that's what kind of comes to mind when you see this mechanism of hurricane propagation through the island. So next slide is about distribution. So cyclonic nature of hurricanes drives a special distribution of moisture on slope, and this is called wind-driven rainfall. This exists also in our paper about Puerto Rico. We have some review of articles about wind-driven rainfall, and if you look at the paper, you'll find a lot of details, a lot of information. But this is how it looks like when you're looking at animation. This is produced by Weather Service, National Weather Service, NOAA, and this is a Hurricane Maria coming to Puerto Rico. So it's a radar, it's reflectivity, so basically correlates with the moisture distribution. And you can see how it's kind of like uneven. So when the eye comes in, different areas get affected, and direction of the wind, direction of that rotation, brings moisture. Again, it's like hosing effect. So it brings moisture from different sides. Like at the beginning, it was coming from here, but as hurricane propagates, so you might expect north, western direction, northeastern direction, southern direction. So the moisture can come to slopes from all different directions. And that's something that is very interesting, I think, for thinking about where landslides can occur. So here is a more detailed information. If you're looking at September 20, so that's when hurricane basically came to Puerto Rico. It was very close. Here is the eye, and it was approaching the island. So the arrows correspond to the wind direction and wind speed. So the highest wind speed, of course, came from this side of the hurricane, from this what's they call quadrat, and affecting Puerto Rico very strongly from northwest. So I'm sorry, northeast. And so then the hurricane was coming over the island, making landfall. You get a lot of moisture here. But now look at directions. So directions now changing. And you can see even here, you can see even direction from south. So there is a variety of directions affecting the island right now. And if hurricane passes through by 6 p.m., so it's already went beyond Puerto Rico, and then the southern direction occur. right? And so they kind of kick in with the moisture distribution, because look at the wind direction here, wind arrow. It's still not very small. It's still kind of big, arrow. So there is some wind going on and putting water on the slopes. And of course, when hurricane leaves the area, then the arrows become smaller and you get less effect from anything. So that's a structure, what happened in Puerto Rico. And the changing wind direction, precipitation definitely affect moisture distribution. So this is example of the same thing, but we take a look at little area here, which is El Yunque National Forest in Puerto Rico. And if you just zoom in and you look at the area of it, so you can see the mountain, little mountains, and this is how wind propagates through, and this is what orographic effect does. So when you get a lot of moisture on specific slopes like this one facing northeast, right, you might expect to have less moisture on slopes facing, let's say, southwest. So this is kind of idea that the distribution of moisture is not going to be the same. And we know that Caribbean region and Central America, it's all mountains. And some of them, like in Guatemala, goes up to 2,000 meters, even more. And Puerto Rico has high mountains. So mountains in kind of combination with wind and precipitation can create this heterogeneous spatial distribution of moisture. So this is sort of, again, idea of what's happening during hurricane activity. And how WDR, wind-driven rainfall, is computed. So there were interesting articles by Guthrie in 2010, and Pike and Sobiezik, both also from USGS. And actually, Sobiezik came to me in AGU and said, thank you very much for bringing the paper and his methodology. But what they did is they developed this equation, which allows you to calculate wind-driven rainfall in 24 hours. So the input into equation are wind-driven rain over 24 hours. It's a hydrologically effective precipitation received at ground surface. And that's the result, right? But you get it from hourly vertical precipitation. So this is a conventionally horizontal oriented rain gauge for any time of interest, or it can be, just GPM, global precipitation data. Here is the terrain gradient slope. Okay, we have a digital elevation model. And this is a B-angular departure of rainfall from vertical. So there are ways using work of these people, Sharon and Erpel, to find out, to calculate B. And of course, terrain aspect. So terrain aspect is one of this very important, I think, issues, very important, parameters which we need to address again because of wind direction. And then, of course, hourly wind direction. So that's also can come, it's a compass direction from which the wind originates. So this is a tool which we can use. Now, a requirement of data. We definitely need antecedent soil moisture condition to apply to the model. And that can come from SMAP, level 2 enhanced passive soil moisture product. It's a 9 by 9 kilometers, excellent product, being tested right now, and people get very good results. Aspect and slope come from SRTM, 30 by 30 meters, and wind direction and speed. That comes from MERA2 data. It's pretty coarse. It's about 50 by 60 kilometers data, but this is what the best available right now. And of course, precipitation coming from GPM. Basically, it's IMERG data, and it's a 10 by 10 kilometers every 3 hours. And hurricane tracks we can get from National Hurricane Center Advisory. So what you see here is the issues. Issues are downscaling and normalizing data and verification, of course. So that's one of the main things which I'm trying to figure out now. I have no answer for that, except that it's possible. We just need to concentrate on that and, sit down at the drafting table and start thinking about all kind of spatial variations which we have and how to normalize it and downscale, and then we can apply it. So, but all this data are available to use in this equation, which which we see here on the screen. So let's move on. Hypothetical algorithm for this kind of project is number one, we need hurricane advisory. It's a wind direction and speed. So that goes to GIS layer, become GIS data set. And then this data, wind and precipitation, goes to computing WDR, wind-driven rainfall. And then you combine your wind-driven rainfall with the slope and aspect of hurricane-affected area to account for orographic effect. And then you also apply antecedent moisture condition to this model. And then altogether it becomes a map, and which shows you potential slopes where landslides can occur. So again, most likely it's going to be, landslides affected by the direct impact of wind and increased moisture in combination with a high antecedent moisture condition. And after you create this map, the product, you can look at proximity of infrastructure, population centers, and then definitely you can pass it to users with a cell phone. So this can be done in real time, and because you have hurricane advisory in real time, you have GPM working in real time, and then you pass information to user to the cell phone. And ideally, you're going to get something like this, that real-time warning system, which can be designed by developing predictive model based on wind-driven rainfall and mobile mapping app. So you start with a hurricane, and then you open your phone, and your phone is going to tell you where potentially landslides can happen. And then you can make decision, are you going to run, are you going to stay, is it close to you or not? So it could be a variety of possibilities with making decision. So I think at this point I'm done. And if you have any questions, please, you're welcome to ask me any questions. So thank you very much for listening.
Thank you, Yuri, very much. And I hand over to Ben for the following discussion.
Great. Excellent work. I'm trying to find my applause button, but others have found it too, so that's great. Does anyone want to start off with some questions for Yuri, or? I have just sort of a technical question. What are the latencies on all the inputs that you would go into something like this, the data inputs, and then the processing needed to turn it into, those various steps?
Basically, again, the antecedent moisture condition you can get in advance. So that's would be something that already exists before hurricane. Aspect and slope, it's already produced and you have it in advance. So this data are, basically exist and sitting on a server. Wind direction and speed every 6 hours. So you would start working with this and with advisories. So the hurricane track and wind direction speed will be, this hurricane track and this would be kind of going together. And I'm sure we have now great models that can you tell how hurricane will proceed. Maybe something is going to happen unusual, like in case of Sandy in New York. But in general, it should work pretty good. And every 6 hours, you can have your wind direction and see where a potential impact is coming. And then you combine this with the 3 hours of precipitation data. So 6 hours here, 3 hours here, and real-time advisory. So in my opinion, if you look at this hours, if data are good, because we know sometimes you download it, you look at them, and they're not good. Something happened, processing is slow. But probably we have sort of like, I don't know, like at least 12 hours of time to predict something. So we can do something in advance, definitely 6 hours before you get a landfall. You know, so this could be done in advance. And yeah, so that's, I don't know if I answer your question.
Yeah, no, that's great. So the thing that is curious to me that with well, all of the hurricanes, but especially the Maria one, is, I mean, if you have this spinning saw blade moving over, shouldn't, in theory, every aspect sort of get the same wind direction at some point in the passage of the hurricane?
What? Yeah.
Move?
Okay. So this is an issue with, you know, with the coarseness of the data, because you know these data are not very fine resolution. So when you take wind directions and you apply them, so you can see still for the island like Puerto Rico, you can have, this is one direction, this is another direction, and this is coming, you see, from south. So it's a good question, and it relates again to normalizing data, how you downscale that coarse wind direction and match it with the terrain, with the aspect. So this is a question. I'm sure in the future we're going to get more high resolution data, but for now we don't have them. So it doesn't mean we can, you know, do nothing, but we can try to apply it. And again, the problem now is how you downscale and normalize. So when we find the way to do it, maybe through some, this is what basically my goal was at presentation at AGU. I'm not expert in atmospheric physics, and I think good physicists who work with meteorology and atmosphere would be very helpful here. Maybe even group of people. So my goal of presentation was basically attract attention to community and find collaborators. So, or, you know, even if you want to take this work on your own, it's fine. I mean, I'm not greedy for whatever, but I think this requires some collaboration and, you know, close look into that process, because it's not a simple thing. But just in general, you can still produce some results with this. So you got wind direction here, you can assume it's going to be the same all over the island. And then when you move here, so, you know, these blocks here, they definitely will create some heterogeneity. You're not going to get the same areas in this area, in this area, in this, and this. So the affected area will be, you know, different in these 4 spots, most likely. I don't know, but this is what I assume, because this arrow goes this way, this goes down, this goes this, and so on. And if you look here, when it passes by, you can kind of predict what's going to happen. So this actually could be also very helpful when hurricane passes the area, because even if landslides didn't happen, there is a high propensity it can happen, because the moisture is still here, but the wind direction is different now. So the moisture coming more from another direction. So there is a propensity, and that might be useful for people, you know, to realize that even when hurricane passes by, there is still potential for landslide to occur. And they have to be cautious. You know, it's like earthquakes, right? So you get a foreshock and you get a strong deformation of the building, but then you don't do anything because you're waiting for aftershocks. So geologists come with equipment and start measuring and looking for a pattern. And the same thing with landslides. You get hurricane passing by, but landslide can happen after, where it's going to happen. So just looking at that picture, for example, here at 6 p.m., you can say, well, guys, you know, you're not safe over there. It might happen. Probability, maybe high or low, I don't know, but it might happen. So I don't know if I answer your question or no.
Yeah, we have also a question here in the working document. It's a question about spatial scales. Over what spatial scales does the hosing effect happen? Hill slope to hill slope, or?
Okay, so precipitation is a 10 by 10 kilometers. So if you combine 10 kilometers pixel of precipitation with, let's say, you know, 50 kilometers wind direction speed, so basically you're going to have the same constant wind direction speed over 50 kilometer pixel, but inside that pixel you're going to get at least 5 different precipitation values. So because this is a higher resolution than wind direction. So wind direction can be ambiguous because it might change, especially also like dealing with the terrain here. So even if it's wind coming from here, you might have low, effect of terrain, local effects. And that's why, again, I need, I feel I need somebody from atmospheric physics to come and take a look at this. But I think that having high resolution precipitation under coarse resolution of wind direction give you enough values to play with. So you can assess soil moisture. And basically, I think idea will be not even to do absolute value, but like high-low moisture content. And then you can divide them into like low, medium, and high. So high will have a higher probability of landslide production. And that's what you combine with the aspect. And then you're going to get location, approximate location, but you're going to get it. I don't know if it makes sense or...
It makes sense. I guess to me, it seems like much coarser resolution than we think about with these processes like orographic effect or aspect interacting with wind on the precipitation. But I guess these would scale up at even a much larger scale for a storm. I think I don't need you to necessarily explain the Pike and Sobeys method, but that accounts just for the kind of slope and wind direction part of it. Is there, how did you integrate the orographic part in?
So orographic is, we have a terrain aspect here. So terrain aspect is the orientation of a slope, right? So if I get my wind direction coming, let's say, I don't know, like say like this is a mountain, right? And you get a wind from here. So most likely the moisture will be here, but it's going to last on the other side. And so the aspect is very important. And I found that many people don't use aspect, but like I showed to you, if you're looking at data, again, it's I don't have all data for, Central America or Caribbean, but Guatemala shows you that there is a pattern of, very specific orientation of the slopes, right? So this is aspect, and here is the same thing. It's aspect plays, big role where you get more landslides or less landslides. And I understand it's not perfect. You cannot pinpoint landslide location, but you can say these slopes will be affected, and then let's map them. And when you map them this is what's going to happen. You map them over SRTM. So you map them at 30 by 30 meter resolution. And so that 30 by 30 is going to give you, pretty interesting numbers. But I mean, not numbers, but locations. However, of course, because of coarseness of wind stuff, like 50 kilometers and precipitation 10, then you're going to get a lot of slopes, which probably will show the same value. So it's very difficult to expect from distribution of landslides to be, very specific location. It's probably going to be like many of them, and they will have the same, numbers of how much moisture you can expect here. And it's due to coarseness of data. But I think the concept itself can be tested, and it shouldn't be very hard to make it. Again, the question is how we can approach normalization of data with different scale, how we can put it all together in one matrix. Like in hydrologic modeling, you take, for example, data on slopes, you take data on, rain, and you create so-called hydrological units. So it's a unit on a map where all hydrological parameters are the same. And so resolution depends on basically digital elevation model. But in this case, you combine a lot of them, trying to create metrics of landslide potential, occurrence of landslides. And so that's what is the goal of it, but we need to get through this hurdle of normalization and bringing it all together. But it looks to me like we have all components ready for the formula, and I'm not sure if this is ideal formula also. So maybe that should be revised. But like I said, I'm not expert in atmospheric physics, so I have a hard time to approach it. I mean, I can try, but it's probably
this,
there are.
This method was developed, I think, on the San Francisco Bay Area, if I remember correctly.
Right.
And it might actually be a more appropriate place to test it, again, with all the recent atmospheric rivers that have hit there, and the resulting landslides. And there's similar events in 2017.
Right.
Because there, really, the fire hose is in one direction. It's not kind of changing as the hurricane passes, but the atmospheric river is sort of pointed. And it may move up and down the coast, but it's pointed at the same topography in the same direction throughout the storm. Yeah.
So there is another question in the working document about the role of the vegetation. Do you see that in these areas that you looked at, the vegetation also plays a specific role, has maybe also a relationship to this wind direction, so that not only the wind is decisive, but also the vegetation?
It's actually an excellent question, and I should say that I kind of omitted this from this presentation, not really intentionally, but because again, we worked with in Puerto Rico, this paper which we wrote. It's very difficult to understand in landslide occurrences. They happen after vegetation is gone. Like, this is kind of idea that vegetation is gone, then slope becomes very weak, and then you get a landslide. But definitely land cover should be included here as well. Yeah, I don't have it here, but it should play some role here, because it can be.
That gets more complicated when you leave the tropics. So the equatorial zone, the aspect is less an issue for vegetation patterns, but in the northern hemisphere, there's a really strong north-south aspect dependent vegetation, and the root strength has a big impact as a result.
Yeah, in a paper from 2016, we actually present several articles about hurricane damages to vegetation, and they also talk about preferential aspect. So the vegetation suffers from very specific directions, and then that's the impact of hurricane cyclonic activity. So there is evidence to that as well, that it get affected by, but definitely in terms of landslides, the USGS report on Hurricane Maria, the lady who was one of the leading scientists there, she wrote that geology is the most important thing, and geology is the same pretty much everywhere, which is basically weathered, bedrock. It's all weathered volcanic material, and that's why you have this debris flows pretty much everywhere in Puerto Rico, in Guatemala, because of this weathered upper part of the crust. Yeah, but definitely vegetation should be part of it. Yeah, I agree. And vegetation now, we used to have data from Maryland to 150 meters resolution, but now at AGU they presented new data set with I think it's 10-meter resolution global land cover for the whole world. I forgot the name of it. I have it in my notes on AGU, so if you send me email, I'll let you know. But it's a great product. It's a new product, and it's available. So that will actually be very good with SRTM, because you got 30 meters elevation, and then you have 10 meters land cover, which is perfect.
Okay, thank you very much, Yuri. So maybe if you could unshare your screen, then we see all others again, and it would be nice, since it's the first meeting of the year, it would be nice if everybody's turning on the video, and then we can see who we are. And that would be then also maybe an opportunity to applaud and thank again to Yuri to this input, which was really different than we had in the previous sessions. We talked a lot about soil moisture, about IoT, different things, but never about wind, actually. Now we would like to say something about how we plan to go on in general with this working group. We have now tested that format for 2 years. We got back a few of comments, and Ben, he will now summarize a little bit our thoughts on that in this respect.
Thanks, Manfred, and thanks everyone for your continued engagement in this working group and part of the community of LandAware. I have certainly in the last 2 years appreciated how well organized and constrained, or I guess well-defined, the objectives and activities of this working group have been, and so I'm excited to help Manfred continue that moving forward. Certainly if there's other feedback, feel free to send that to both of us about other ideas in which we might innovate this innovations working group, but overall it seems to be going really well in terms of sort of having these regular online gatherings that bring our community together and revolve around sort of one invited presentation on one innovation and some discussion, and then you know, on a new theme. We recognize that the pace that we may not be able to have constant innovations to present in the that they require the people out there to be making some innovations. So we don't really want to have a defined number of meetings, but when we learn of something, and if you have an idea or learn about an innovation that you'd like to see shared with the community, please pass that on to us. And the one experiment that we propose trying this year is that in addition to sort of having one themed discussion and topic, there's such a wealth of experience and expertise and opinions within this group. We thought it might be nice to end some meetings with informal pop-ups related to kind of in progress or harebrained ideas for innovations that you'd like feedback or engagement with us on. We thought we would try this out at the end of every meeting, and similar to the news section if you have an announcement, but in this case, if you have an idea or start of a paper or the start of a collaboration or method that you want to get feedback on or get out there, that this is a nice supportive group of people to do that with. So we won't, if anyone has any today, it's very much on the spot, and you're welcome to do that now. We've got another half hour scheduled on the meeting, but otherwise we were going to propose to do something like that at the end of every meeting, and you can prepare a slide or two or not prepare anything, to sort of present ad lib, but we wanted to make some space for a little bit more unpolished work to be presented and shared in this format, since that's sort of the spirit of innovation. So with that, that's sort of our plan for 23-24, and if it doesn't wind up being a format that people want to use, then we can just revert back to what we know has worked so well the last 2 years.